Okay, welcome to arguably the most difficult chapter um, of the course for Pure Maths, which is integration. So, year two integration. Um, this is more about the how than the why for integration. So, what do I mean by that? I mean, you've already seen that integration can be used to find the area under a curve or between curves and sort of so on. Um, that's an application of it. That's why. So, how I'm going to talk about rules to deal with more difficult situations and so on. So, it's a big chapter, first of all. And these are some of the things that we're looking to do. So, standard results, what this one's all about, which is our first lesson, is how if we think about differentiation, tan is sec squared. So, by knowing that tan becomes sec squared, you can, instead of differentiating, you can integrate um, as long as you remember the C. Okay, that's the first one. We've got something over here called reverse chain rule. This one, you don't need to get bogged down with this one too much. If you're on the further maths route, you want to be able to do this one quite quickly. And some of you might naturally like this one, but don't be worried if this one doesn't click straight away, because actually, these questions can be done using substitution, and substitution is sort of a bigger technique that we'll look at. We make substitutions. X's become U's typically, and so on. And this can help us to integrate. So if reverse chain rule is very tricky, don't worry, that can actually be done by substitution. So this is one of the big techniques, I suppose. And then integration by parts is sort of like using product rule in reverse. Again, it's another one of the big techniques. Okay, so this is sort of a memory thing. This is one of our first big techniques. Second big technique. So this is why it's a big chapter. Integrating partial fractions. So this is all going to be about linking to chapter one and also to logs. Okay. Approximating areas using the trapezium rule. You might remember at GCSE, we talked about finding the area under a curve by making lots of trapezia. Interestingly, that's in year 13. It's a rule, it's put in your formula booklet, so it's quite a nice sort of reprieve from some of the harder stuff in here. And this is effectively what we're doing when we integrate, really. We're using trapezia that get smaller and smaller, infinitesimally wide, and that's what we're doing. And then finally, quite challenging, we're going to be solving differential equations. Okay. Often there's some sort of connection with partial fractions, not always. And this one here requires its own technique. There's also some stuff in here about rates of change from differentiation. So this one's going to bring everything together. Don't worry though, we'll break it up part by part. So let's get started first of all. This is my y, my function, sort of whatever it is. And this is when I integrate it. So where can x to the n come from? So in other words, how do you integrate something like x cubed? Well, if you remember, we increase the power by 1 and we divide by the new power. This is just the formal way of saying that. You increase it by 1 and then you divide by that. You also have that constant of integration on the end. Yeah. E to the x, think about differentiation with e to the x. E to the x is e to the x, so just the plus c. And before I reveal these ones here, I want you to think about your differentiation from before and think about what differentiates to these things. Because you just need to do the reverse of it and you need to add the c on to the end. So assuming you've done that, we're looking here for the natural log of x. We have to put these, the natural log of the absolute value of x. We have to put this absolute value around here because otherwise we end up with issues and it's not defined. Like you can't have log of a negative number. So one to remember there, it's got these these gates on here. And we'll look at how to deal with that later. Cos came from sine. Sine came from minus cos. What differentiates to sec squared? If you've been listening and you've been following closely, you should know this result because this is one that I said needs to be burnt into your brain, essentially. It's tan, okay? Tan sec squared. The other one we talked about was what became sec tan, and it was sec, Okay, so I would expect you to have some awareness of all of those leading up here. Now, these ones, what we've said before is we've said think about sort of the basic versions without co and then adding co, what that does. So you add cos and there's a sign change. So instead of that being tan, it's cotan or cot, and there's a sign change. And a similar thing is going to go on with these ones here. So we're adding cos. So we're going to add cos and we have a sign change. And that's how, if you remember your differentiation very closely and you remember the cos and sign change thing, that's how you can know those results there. Okay. Because believe it or not, we are quite happy when we see these results and we're being asked to integrate because we know already what it should be. Sectan. So, in fact, how about I give you just a moment to look at them, check that you can answer, pause the video, and then I reveal. So, sectan came from sec plus c. Sine came from minus cos plus c. Cosec, well, this is like sec squared, which comes from tan, but you're adding the cos, so cotan, cot, and a negative. So it seems like a lot. That's the point where you need to get to, okay? That you know these derivatives and antiderivatives like this, okay? Same again, pause the video, have a think. Okay, and sec squared came from tan. This here, it's like sectan, but with the cos. Sectan came from sec, so cosec with the sign change. Don't forget those lines there on the x, the absolute value of x, and so on. We've got a couple more, so for the last time, pause the video here and have a quick go. Okay, and we've got our answers there. So in reality, they don't often appear just on their own. They might appear sort of as a longer integral. So here, for example, if they're separated by plus and minus signs, you can handle them each in turn. Okay, you can. This is the same as doing this effectively. So cos, well, that was 2 sine, wasn't it? This one over here, a bit easier in my opinion if you think of this as 3 times 1 over x. Yeah. And then numbers sort of sit out the front when you have scalar numbers sort of at the front, just scaling 1 over x up and down and so on. Just leave them at the front and deal with this part here. That's my advice. As always, easier as well if you change this to index form. So look, there's a bit of year 2 integration mixed in with some year 1 integration there. Okay, and this is what we would be looking for. Hopefully you see that, my opinion, that makes this integration much, much nicer if you keep that 3 out at the front, because then it sits in front of the natural log of the absolute value of x. Don't forget the plus c. Easily done when it's convoluted. Cos and sine and so on. Now, often we like working in cos and sine and we turn tan and cot into this. But the reciprocal functions are sort of your friend now because you know identities and you know derivatives and antiderivatives. So if you break this up into cos times cos over sine, you might think, so what? But if you rewrite that, you've actually got cos x cot cos x cot x, and you're integrating this one here. Okay, cos over sine, cos over. Sorry, I was going to say it doesn't sound right. That should be a 1 over sine, shouldn't it? Yeah, check that it actually takes you back to the answer. So 1 over sine, sorry, that's not cos. I was going to say it doesn't sound right. So over sine, that should be cosec. So we've got sec x tan x with the cos on it. Sec x tan x becomes sec. So with the cos, it must become cosec with the sign change. Okay. So actually, it was good to write this using reciprocal functions. I mean, things with cos. It was good to write them because there's a standard result that we can use there. Yeah. Another challenge is you might look at this, and when you learn more rules, you might vastly overcomplicate this. But when we have one term in the denominator, um, like so, we can sort of add fractions in reverse. So that's the same as 2x over x plus 1 over x. And if you're not sure, I would ask you just to add that together and you will see that it does in fact give you this. So that's the same as 2 plus 1 over x. And then this is one of these questions where we want to integrate. So you still need to integrate. We haven't actually integrated yet. You'd still want to integrate that one there. You'd put in your limits and look, the answer's there, natural log. I can also see that natural log sort of makes sense because I can see a 1 over x here. So I can see there's going to be some natural log stuff. I'll pause the video for you to have a go finishing off that question there. I think it uses some log rules. So just pause the video and have a go before it's revealed. Okay, so let's take a look. So we integrate to this one here. We put our limits in. You must always integrate the algebra, by the way. This is an aside because I know you can't do this with your calculator, but even if the calculator gives you the number, you need to actually show the algebraic integration and the limits going in, and then a subtraction of the upper limit from the lower limit. You have to show that. That's not optional, okay? But we sort of end up in a situation like this. You've got a log on the left and a log on the right, and by doing it this way or however, you should be able to sort of combine these ones together. So I think I would, at this point here, I would take away the log 3 and I would say natural log 12 minus natural log 3. And remember, if the base is the same, when you subtract, that's the same as division. So 12 over 4, 4a. Okay, that's the way that I would do it. But anyway, there you go. So we're using those standard results, which is what the first part is all about. So you should now be in a position to have a go at 11a. A couple of bits of advice there that we've discussed through the video as well to keep in mind when you're doing this.